Last time we used row operations to solve a linear system. Today we explain why every row operation is really left multiplication by a special matrix called an elementary matrix. Yes, even swapping rows gets its own matrix. Linear algebra is very committed to putting everything in rectangular packaging. The 3 row operations are: swap 2 rows, scale 1 row by a non-zero scalar, and add a multiple of 1 row to another row. Today we turn these operations into matrices, because apparently operations were not official until they had entries. An elementary matrix is made by applying one elementary row operation to the identity matrix. Start with the identity matrix IM. Perform one row operation on IM. The result is an elementary matrix E. The key fact is, multiplying E times A on the left performs that same row operation on A. So row operations are not separate magic tricks. They are matrix multiplication in disguise. Because apparently disguise was still available. Why left multiplication? Because left multiplication combines rows. Think of A as a stack of rows, row 1, row 2, down to row m. The row indexed by I of EA is a linear combination of the rows of A, using row I of E as coefficients. That is why row operations are left multiplication. Right multiplication would affect columns. And that is a different little disaster for another day. First example, swapping rows. To swap rows 1 and 3, start with I3 and swap rows 1 and 3. This gives P13. If A has rows R1, R2, and R3, then P13 times A swaps row 1 and row 3. The matrix does exactly what the row operation did. Stunningly literal. A rare kindness from notation. Second example, scaling 1 row. To multiply row 2 by C, where C is non-zero, use a diagonal matrix with C in the second diagonal position. Multiplying D2 of C times A leaves row 1 and row 3 alone, and turns row 2 into C times row 2. We require C non-zero because scaling a row by 0 destroys information. Algebra dislikes irreversible vandalism. Third example, add a multiple of one row to another row. For row 3 replaced by row 3 plus C times row 1. Put C in position 3, 1 of the identity matrix. Then E31 of C times A leaves the first 2 rows alone, and changes row 3 to row 3 plus C row 1. This is the row operation we used during elimination. Now it has a matrix costume. Try to act surprised. Let us summarize the general patterns. A row swap is represented by a permutation elementary matrix Pij. A row scaling operation is represented by Di of C with C non-zero. A row replacement operation is represented by Eij of C, which adds C times row j to row I. Every elementary row operation is left multiplication by one of these elementary matrices. Now the most important point, every elementary row operation is invertible. Swapping the same 2 rows again undoes the swap. Scaling row I by C is undone by scaling row I by 1 over C. Adding C times row j to row I is undone by adding negative C times row j to row I. Therefore every elementary matrix is invertible. Row operations are reversible, not just algebraic graffiti. This is why elementary matrices will keep appearing in the next few videos. A sequence of row operations is the same as multiplying on the left by a sequence of elementary matrices. Since each elementary matrix is invertible, these operations preserve important information. For example, AX equals 0 if and only if EAX equals 0, because E is invertible. This will help us justify Gaussian elimination, rank, nullity, inverse computations, and later determinant calculations. Tiny matrices, suspiciously large consequences. Let us summarize before the elementary matrices start acting important, which unfortunately they are. An elementary matrix is the identity matrix after one elementary row operation. Multiplying EA on the left performs that row operation on A. The three types are row swaps, row scalings, and row replacements. Every elementary matrix is invertible, so row operations are reversible. Next time, we will use this machinery to make Gaussian elimination more systematic, because apparently solving equations by hand was not bureaucratic enough.